Everyone thinks Yellowstone is the most dangerous volcano on Earth. They're wrong. Yellowstone is a firecracker compared to what actually happened to this planet once before. 252 million years ago, Siberia didn't explode. It bled. For 1 million years, lava poured from a wound in the Earth's crust the size of Europe. The volume? 4 million cubic kilometers. That's 1,000 Yellowstones, erupting continuously for 1 million years. Imagine standing in Siberia as the ground splits open. Not a mountain exploding, a crack extending to the horizon in both directions, fountaining lava day after day, year after year, century after century. The sky turns black with ash. The oceans turn to acid. The air fills with poison. 96% of all life on Earth died, not from the lava, from what the lava released into the atmosphere. And here's the terrifying part. We're doing the same thing right now, just 2,000 times faster. Before we dive in, please consider subscribing and liking this video. Your support truly helps us continue this work. Thank you. So what was the largest volcanic eruption in history? The answer depends on how you measure largest. By explosive power, Yellowstone's Huckleberry Ridge eruption 2.1 million years ago. 2,500 cubic kilometers ejected in a matter of weeks. The most powerful explosive eruption we know of. By total volume of lava, the Siberian traps 252 million years ago. 1 to 4 million cubic kilometers, 1,000 times more material than any supervolcano. By death toll, also Siberian traps, 96% of all marine species, 70% of land vertebrates, the worst mass extinction in Earth's history. Today, we'll explore all three, but we'll focus on Siberia because it wasn't just the largest, it was the deadliest. And the mechanism that killed almost all life on Earth? We're repeating it right now, just 2,000 times faster. Let me show you why that should terrify you. Let's start with what most people think of as big eruptions. Mount Vesuvius, 79 AD, buried Pompeii under ash, killed thousands of people in a matter of hours. That was a VEI 5. VEI stands for Volcanic Explosivity Index. It's a logarithmic scale, like the Richter scale for earthquakes. Each step up represents 10 times more ejecta. Vesuvius was catastrophic for the humans who lived near it. In geological time, a footnote. Krakatoa, 1883. The explosion was heard 4,800 kilometers away, the loudest sound in recorded history. The pressure wave circled the globe 7 times. 36,000 people died, most from tsunamis generated by the volcano's collapse. That was a VEI 6, 10 times more powerful than Vesuvius. Tambora, 1815. You might not know the name, but you know what it did. The year without a summer. Global temperatures dropped. Crops failed across Europe and North America. Mary Shelley wrote Frankenstein during the cold, dark summer trapped indoors. Byron wrote Darkness, a poem about the end of the world. They didn't know it, but they were living through the aftermath of the most powerful eruption in recorded history. VI 7. 100 cubic kilometers of material ejected. 100,000 people died, most from starvation in the years that followed. These are planet-altering events. But a supervolcano? That's VEI 8. 1,000 cubic kilometers of material or more. Enough to bury entire countries under meters of ash. Enough to change the climate for decades. Enough to threaten civilization itself. The difference between a normal volcano and a supervolcano isn't just size, it's mechanism. Picture a normal volcano, a cone-shaped mountain with a vent at the top. Magma rises through a conduit and erupts, building the cone higher over thousands of years. Mount Fuji, Mount Rainier, Mount St. Helens. These are stratovolcanoes. Now picture a supervolcano. There's no mountain. Instead, there's a magma chamber, a vast underground reservoir of molten rock, sitting just a few kilometers below the surface. This chamber can be tens of kilometers across. As magma accumulates over hundreds of thousands of years, the ground above it bulges upward. Pressure builds. Eventually, the roof of the chamber cracks. When it does, the entire chamber can empty in a matter of days or weeks. But instead of building a mountain, the ground collapses into the void left by the evacuated magma. What you get is a caldera, a vast circular depression that can be tens of kilometers wide. Yellowstone is a caldera. So is Lake Toba in Indonesia, Long Valley in California, Taupo in New Zealand, the Valles Caldera in New Mexico. Each one represents a catastrophic eruption that reshaped entire regions. Long Valley, for example, erupted 760,000 years ago, creating a caldera 32 kilometers long and 17 kilometers wide. The Bishop Tuff, the ash and rock ejected during that eruption, covers much of eastern California and Nevada to depths of hundreds of meters in places. Taupo in New Zealand last had a supervolcanic eruption 26,500 years ago. It ejected 1,100 cubic kilometers of material. Maori oral traditions, passed down over thousands of years, describe the sky turning red and darkness lasting for days. These aren't mountains, they're scars, the collapsed roofs of emptied magma chambers. And when they erupt, they don't just threaten a region, they threaten the entire planet. Let me give you a sense of scale. When Long Valley erupted 760,000 years ago in eastern California, it ejected 600 cubic kilometers of material in a matter of days. The Bishop Tuff, the volcanic deposit from that eruption, covers over 3,000 square kilometers to depths exceeding 100 meters. Ash from the eruption has been found in Nebraska, over 1,000 kilometers away. The caldera it created is 32 kilometers long and 17 kilometers wide. If you visit Mammoth Mountain today, a popular ski resort, you're standing on the rim of that ancient caldera. The mountain itself is a volcanic dome that grew inside the collapsed crater hundreds of thousands of years after the main eruption. And beneath it, magma still churns. The area experiences frequent earthquake swarms and significant carbon dioxide emissions from the soil. Enough CO2 that trees in some areas have died from root asphyxiation. Long Valley isn't extinct, it's dormant, and geologists monitor it continuously. Taupo in New Zealand has an even more dramatic recent history. The Orowanui eruption, 26,500 years ago, ejected 1,100 cubic kilometers of material, making it one of the largest eruptions in the last 100,000 years. But Taupo didn't stop there. In the year 181 AD, it erupted again. This time, it was only a VEI-6, much smaller than the super eruption, but still massive by human standards. 120 cubic kilometers ejected. The eruption column reached 50 kilometers into the stratosphere. The sky over China turned red. Roman and Chinese historical records both mention unusual atmospheric phenomena that year. Blood-red skies, diminished sunlight. They didn't know the cause was a volcano on the other side of the world. The Taupo eruption created pyroclastic flows that traveled up to 90 kilometers from the vent at speeds exceeding 300 kilometers per hour. Everything in their path was incinerated. And yet, because the region was sparsely populated at the time, the human death toll was relatively low. Had it happened today, with the surrounding area now home to hundreds of thousands of people, the devastation would be unimaginable. The Valles caldera in New Mexico, formed 1.25 million years ago, is another example. The eruption ejected 600 cubic kilometers of material, creating a caldera 22 kilometers across. The volcanic field remains active. Hot springs, fumaroles, and small earthquakes are common. The entire region is a resurgent dome, meaning the floor of the caldera has been pushed upward by magma intrusion below. If you hike through the Valles caldera today, you're walking across ground that's rising at a rate of millimeters per year, the heartbeat of a sleeping giant. And then there's Campi Flegrei, the Phlegraean fields near Naples, Italy. This caldera formed 39,000 years ago in an eruption that ejected 200 cubic kilometers of material. It's not as large as Yellowstone or Toba, but what makes Campi Flegrei terrifying is its location. 500,000 people live inside or near the caldera. The city of Naples, with a metropolitan population of over 3 million, sits just a few kilometers away. And Campi Flegrei is restless. The ground has been rising and falling, a phenomenon called bradyseism, since Roman times. Between 1982 and 1984, the ground rose by 1.8 meters. 1.8 meters in 2 years. That's not normal geological uplift. That's magma moving beneath the surface. Tens of thousands of people were evacuated from the town of Pozzuoli as buildings cracked and the land deformed. The crisis passed without an eruption, but it was a warning. Campi Flegrei is not extinct. It's one of the most closely monitored volcanic systems in the world, precisely because an eruption there would be catastrophic on a scale difficult to comprehend. A VEI 7 eruption at Campi Flegrei would bury Naples under meters of ash, kill millions, and disrupt the entire Mediterranean region for decades. The point is this: supervolcanoes are real, they're geologically recent, and they're still active. But the key word is geologically. On human timescales, they're extraordinarily rare. The recurrence interval for VEI 8 eruptions globally is roughly every 50,000 to 100,000 years. Compare that to the certainty of climate change impacts this century, and the priorities become clear. But here's what most people don't know. The most catastrophic volcanic event in Earth's history wasn't a supervolcano at all. It was something worse. 74,000 years ago, in what is now Sumatra, Indonesia, the Earth's crust gave way. Lake Toba erupted. 2,800 cubic kilometers of rock, ash, and gas launched into the atmosphere in a matter of days. To put that in perspective, imagine taking all the Great Lakes, Superior, Michigan, Huron, Erie, Ontario, and converting them to volcanic ejecta. That's Toba. The explosion was heard across the Indian Ocean. Ash fell across South Asia, 15 centimeters deep in India, 2,000 kilometers away. Malaysia was buried under 9 meters of ash. 9 meters. Entire ecosystems were smothered instantly. But the ash wasn't the killer. It was what came next. Sulfur dioxide, millions of tons of it, injected into the stratosphere. At that altitude, SO2 combines with water vapor to form sulfuric acid aerosols. These tiny droplets are incredibly efficient at reflecting sunlight back into space. Within weeks, global temperatures plummeted 3 to 5 degrees Celsius. That might not sound like much, but consider the difference between the climate today and the last ice age is only 5 degrees. Toba created a volcanic winter that lasted 6 to 10 years. In the tropics, temperatures dropped below freezing at night. In higher latitudes, summers disappeared entirely. Plants that survived the ashfall couldn't photosynthesize under the darkened sky. Herbivores starved. Predators followed. But the most dramatic impact was on one species in particular: us. In 1998, anthropologist Stanley Ambrose proposed the Toba catastrophe theory. By analyzing human mitochondrial DNA, genetic material passed down from mothers to children, Ambrose and other geneticists discovered something startling. All humans alive today descend from a population that went through a severe bottleneck approximately 70,000 years ago. How severe? Between 3,000 and 10,000 individuals. 3,000. The entire human species, which had spread across Africa and into parts of Asia, was reduced to the population of a small town. We were on the brink of extinction. Genetic diversity plummeted. Every human alive today carries the signature of that bottleneck in their DNA. We are, quite literally, the descendants of those who survived Toba. The evidence is written in our genes. Studies of Y chromosome diversity and autosomal DNA show the same pattern: a dramatic reduction in genetic variation around 70,000 years ago, followed by a slow recovery as populations expanded again. We almost didn't make it. Archaeological evidence supports this. Sites across India show a layer of Toba ash, and above that ash layer, evidence of human activity vanishes for centuries. In Africa, tool technologies show a sudden simplification around the same time. Fewer types, cruder construction. It's the signature of a population crash. Small, isolated groups, losing cultural knowledge as they struggled to survive. Toba nearly ended us before we ever built a city, invented writing, or left Earth. It was the closest humanity has ever come to extinction. And yet, Toba was not the most powerful volcanic event in Earth's history. Not even close. 2.1 million years ago, in what is now Wyoming, the ground began to shake. Earthquakes intensified over months, possibly years. The land bulged upward as magma accumulated beneath Yellowstone. Then, catastrophically, the crust failed. The Huckleberry Ridge eruption ejected 2,500 cubic kilometers of material, nearly as much as Toba, but with even greater explosive force. Ash spread across the western United States. Identifiable layers have been found as far east as Iowa, as far south as Texas. The caldera formed by the collapse was massive, over 100 kilometers across in places. But here's what's remarkable. Yellowstone has done this 3 times. Huckleberry Ridge, 2.1 million years ago, was the largest. The Mesa Falls eruption, 1.3 million years ago, ejected 280 cubic kilometers. And the Lava Creek eruption, 640,000 years ago, ejected 1,000 cubic kilometers and created the modern Yellowstone caldera, the one tourists visit today, largely unaware they're standing inside a volcanic crater 90 kilometers long and 40 kilometers wide. Beneath Yellowstone right now, a magma chamber sits 8 kilometers below the surface. It's not a single chamber, but a complex system. An upper chamber about 10 kilometers deep, and a deeper reservoir extending down perhaps 50 kilometers. Ground-based GPS stations monitor the caldera continuously. The ground rises and falls like the planet is breathing. Some years, it swells by 7 centimeters. Other years, it subsides. Earthquakes are constant. Thousands per year, most too small to feel. This isn't unusual. It's what active volcanic systems do. The question everyone asks, when will Yellowstone erupt again? The honest answer, we don't know. Yellowstone erupts on average every 600,000 to 800,000 years. The last eruption was 640,000 years ago. Are we overdue? Statistically, perhaps. But volcanic systems don't operate on schedules. The probability of a VEI-8 eruption at Yellowstone in the next 100 years is estimated at 0.00014%, 1 in 700,000. But let's imagine it happens tomorrow. What would occur? Within minutes of the eruption beginning, 90,000 people, visitors and residents in the immediate area, would die. Pyroclastic flows would incinerate everything within a 100-kilometer radius. A pyroclastic flow is not lava. It's a ground-hugging avalanche of superheated gas and rock fragments moving at hundreds of kilometers per hour. Temperature, 700 degrees Celsius. Nothing survives. Ash would blanket 10 states under a meter or more. Montana, Wyoming, Colorado, buried. Crops would fail across the central United States. Ash clogs machinery, collapses roofs, contaminates water supplies. Livestock would die from inhaling abrasive particles or from starvation as pastures are buried. Within weeks, the United States would face a food crisis. Within months, a global one, as the world's largest grain exporter collapses. Sulfur dioxide in the stratosphere would lower global temperatures by 1 to 3 degrees Celsius for a decade. It would be the end of the United States as a superpower, but it would not be the end of the world. Humanity would survive, diminished but intact. Because Yellowstone, as devastating as it would be, is a firecracker compared to what happened in Siberia 252 million years ago. The Siberian traps are not a supervolcano. There's something worse. To understand what happened, you need to understand flood basalts, a type of volcanic event so massive and prolonged that it doesn't fit our usual categories. Imagine the Earth's crust not as a solid shell, but as a thin skin floating on a molten interior. Deep beneath that skin, in the mantle, plumes of superheated rock rise like thermal updrafts. When one of these plumes, a mantle plume, reaches the base of the crust, it can melt through. Not in one spot, but across hundreds or thousands of kilometers. The result isn't a mountain, it's a fissure, a crack in the planet's skin that extends as far as the eye can see. And from that fissure, lava pours. Not explosively, not for days or weeks, for millennia. 252.28 million years ago, Siberia split open. The area affected was 7 million square kilometers, roughly the size of Australia. Lava erupted from fissures stretching across what is now central Russia. The volume of lava, between 1 and 4 million cubic kilometers. To put that in perspective, if you took every volcano that has erupted in recorded human history, every eruption from Vesuvius to Pinatubo to Eyjafjallajökull, and added them all together, they wouldn't equal 1% of the Siberian traps. 1%. The lava flows were so thick, up to 3 kilometers in places, that they're still visible today as vast plateaus of basalt. But the lava itself wasn't the killer. It was what the lava burned through on its way to the surface. Beneath Siberia lay vast deposits of coal, compressed remains of forests from the Carboniferous period, hundreds of millions of years old. As magma intruded into these coal beds, the coal ignited. The carbon stored in those ancient forests, carbon that had been locked away underground for eons, was released as carbon dioxide, trillions of tons of it. And it didn't stop there. The magma also intruded into salt deposits, layers of halite and other evaporate minerals. When heated, these released chlorine and bromine gases, halogens, ozone-destroying chemicals. The Siberian traps didn't just erupt lava. They set the planet on fire from the inside and poisoned the atmosphere with the exhaust. And this didn't happen over days or weeks. It happened over 1 million years. Let me take you back to that world. 252 million years ago, the end of the Permian period. Earth looks nothing like it does today. All the continents are fused into a single supercontinent, Pangaea. One vast landmass stretching from pole to pole, surrounded by a single ocean, Panthalassa. The climate is warm. There are no ice caps. And life? Life is strange. On land, you'd encounter creatures that fit no modern category. Gorgonopsians, saber-toothed predators the size of lions, but not mammals, not reptiles. Something in between, with sprawling limbs and powerful jaws lined with differentiated teeth. They're synapsids, the ancestors of mammals, but they still lay eggs and have scaly skin. Let me tell you about these creatures in more detail, because they represent something extraordinary in the history of life. Gorgonopsians evolved from earlier synapsids, the group that would eventually give rise to mammals. But they developed something remarkable for their time. Their teeth were differentiated, incisors at the front for gripping prey. Massive canines, sabers that could reach 10 centimeters in length in the largest species like Inostrancevia, and cheek teeth, post-canine teeth that could process meat. This is the dental pattern you see in modern carnivorous mammals like lions and wolves. But Gorgonopsians evolved it 50 million years before the first true mammals appeared. Why does this matter? Because differentiated teeth suggest a high-energy lifestyle. You don't need specialized teeth unless you're processing large amounts of food efficiently. And you don't process large amounts of food unless you have a high metabolic rate. The evidence suggests Gorgonopsians were approaching warm-bloodedness, endothermy. They were likely active hunters, not sit-and-wait ambush predators like most modern reptiles. Fossil trackways from the Karoo Basin in South Africa show Gorgonopsian footprints alongside Dicynodont prints. The gait patterns suggest an efficient, possibly semi-upright posture. The stride length indicates sustained locomotion. These weren't sluggish, cold-blooded reptiles that had to bask in the sun for hours before they could hunt. They were active predators that could pursue prey across long distances. The skull structure tells us even more. The temporal fenestrae, openings in the skull behind the eye, were large, providing attachment points for powerful jaw muscles. Bite force estimates for large Gorgonopsians, like Lycanops, suggest they could deliver crushing bites comparable to modern big cats. And those saber teeth weren't just for show. Analysis of wear patterns indicates they were used to deliver killing bites to the throat or belly of prey, severing major blood vessels. It was an efficient killing strategy that would later be independently evolved by saber-toothed cats millions of years in the future. Their prey, the Dicynodonts, were equally remarkable. The name Dicynodont means two dog teeth. Most species had a pair of tusks protruding from the upper jaw, often sexually dimorphic, with males having larger tusks than females. But the rest of the mouth was toothless, covered instead by a horny beak like a turtle's. This beak was used to crop vegetation, tough, fibrous plants that dominated Permian landscapes. Dictynodonts ranged enormously in size. Diictodon was rat-sized, living in burrows and probably feeding on roots and tubers. Moschops was cow-sized with a massively thickened skull. The males likely headbutted each other in dominance displays. And Lisovizia, which survived into the late Triassic, was elephant-sized, the largest non-mammalian synapsid that ever lived. But it was the medium-sized dicynodonts, animals like Lystrosaurus and Cysticephalus, that would prove most important for survival. These were burrowers. Fossil burrows from South Africa show extensive tunnel systems, some extending several meters underground with multiple chambers. These burrows served multiple purposes. They provided refuge from predators. They offered protection from temperature extremes, critical in the increasingly harsh climate of the late Permian. And crucially, they would provide shelter during the extinction itself. When atmospheric toxins were at their worst, when UV radiation was scorching the surface, burrowing animals could retreat underground. That's why Lystrosaurus survived when almost everything else died. In the oceans, the dominant creatures were equally alien to modern eyes. Trilobites had been crawling across the seafloor for 270 million years by the end of the Permian. Think about that timescale. Trilobites first appeared in the Cambrian explosion around 540 million years ago. They'd survived the initial diversification of complex life. They'd survived the Great Ordovician biodiversification event. They'd survived 4 mass extinctions. The late Ordovician extinction that killed 85% of marine species, the late Devonian extinctions, and 2 smaller events in the Carboniferous. Each time, trilobite diversity crashed, but they recovered. They evolved new forms, new ecological strategies. By the Permian, they were less diverse than in their heyday, but still successful, still present in every ocean, still filling important ecological roles as scavengers and predators. Their eyes were technological marvels. Trilobite eyes were made of calcite, the same mineral as their exoskeletons. Each eye was a compound eye made of hundreds of individual lenses, each lens a precisely oriented calcite crystal. These lenses had to be oriented correctly to avoid double images caused by the birefringent properties of calcite. Somehow, trilobites evolved the ability to grow optically perfect lenses 500 million years ago. Modern arthropods like insects have compound eyes made of organic materials. Trilobites invented a completely different solution using mineralized lenses. And it worked for 250 million years. Until it didn't. Until the oceans acidified and the water became toxic and there was nowhere left to go. The Permian reefs were equally remarkable and equally doomed. Unlike modern coral reefs built by scleractinian corals, Permian reefs were constructed by a variety of organisms working together. Rugose corals, wrinkled corals, with a distinctive pattern of radiating septa, formed frameworks. Tabulate corals, colonial corals with horizontal partitions, filled in gaps. But the main reef builders were sponges and bryozoans. Glass sponges, hexactinellids, built massive calcium carbonate skeletons. Bryozoans, tiny colonial animals often called moss animals, formed encrusting sheets over the reef structure, and calcified algae cemented it all together. These reefs stretched for thousands of kilometers along the coastlines of Pangaea. They were biodiversity hotspots. Brachiopods, shelled animals that superficially resemble clams but are not mollusks, lived attached to reef surfaces or buried in reef sediments. Crinoids, sea lilies, echinoderms related to starfish, waved their feathery arms in the currents, filtering plankton from the water. The reefs were thriving ecosystems, billions of years in the making, representing countless evolutionary experiments in how to build a successful marine community. And in a few 100,000 years, they would all be dead, dissolved by acidic water, suffocated by anoxia. It would take 10 million years before reefs returned to Earth's oceans. Now picture what happened when the Siberian traps began erupting. At first, the changes were local. Lava flows buried forests in central Siberia. Ash clouds darkened regional skies. Animals migrated away from the eruption. But the eruptions didn't stop. Fissures kept opening. Lava kept flowing. And the gases, carbon dioxide, sulfur dioxide, chlorine, bromine, began to accumulate in the atmosphere. Let me give you a timeline, because the extinction didn't happen in an instant. It unfolded in phases over hundreds of thousands of years, each phase building on the last until the cascade of death became unstoppable. Phase 1 spans roughly the first 10,000 years after the Siberian traps begin erupting. The fissures open across central Siberia. Lava flows pour across the landscape, burying forests and turning vast areas into basaltic plateaus. Ash clouds darken regional skies. Carbon dioxide and sulfur dioxide begin accumulating in the atmosphere. But at this stage, the effects are mostly local. Global temperatures rise by perhaps 1 or 2 degrees, noticeable in climate records, but not catastrophic. Ecosystems far from Siberia continue functioning normally. Most species don't notice anything is wrong yet. Phase 2, from 10,000 to 50,000 years after eruption onset, is when the global effects become undeniable. Atmospheric CO2 has doubled from pre-industrial levels of around 400 parts per million to 800 parts per million. Global temperatures have risen by 4 degrees Celsius. The climate of Pangaea is shifting. The already arid interior is experiencing mega-droughts. Wildfires are increasingly common. Plant communities are in flux. Species adapted to cooler, wetter conditions are dying back, while heat-tolerant, drought-resistant species are expanding. But this is still within the range of normal climate variability over geological time. Ecosystems are stressed, but they're adapting. In the oceans, the first warning signs appear. Coral reefs in tropical latitudes are experiencing bleaching events as temperatures exceed their tolerance ranges. Ocean pH is beginning to drop as atmospheric CO2 dissolves into seawater. Some species of brachiopods and mollusks, particularly those with thin shells, are showing population declines. But there hasn't been a mass die-off yet. Life is under pressure, but it's holding on. Phase 3, from 50,000 to 200,000 years, is when the system tips past its breaking point. This is the phase of cascading collapse. Atmospheric CO2 has reached 1,500 to 2,000 parts per million, triple or quadruple pre-industrial levels. Global temperatures have risen by 8 degrees Celsius. The tropics are uninhabitable for most land vertebrates. Daytime temperatures regularly exceed 50 degrees Celsius. There's no escape. Pangaea's interior is thousands of kilometers from any moderating ocean influence. Forests across much of the supercontinent have collapsed, replaced by scrubland dominated by seed ferns and early conifers adapted to fire and drought. In the oceans, pH has dropped to 7.8 or lower. Calcium carbonate shells are dissolving. Reef-building organisms can't keep up with the rate of dissolution. The reefs are dying. Trilobites, which have survived 4 previous mass extinctions, are in sharp decline. Their calcium carbonate exoskeletons are vulnerable to acidification. Oxygen minimum zones are expanding rapidly as warming water loses its ability to hold dissolved oxygen. The first blooms of sulfate-reducing bacteria appear in deep ocean basins where oxygen has been depleted entirely. Hydrogen sulfide is beginning to accumulate, and crucially, this is when the ozone layer begins to fail. Chlorine and bromine released from Siberian salt deposits have reached the stratosphere in sufficient quantities to catalyze ozone destruction. UVB radiation reaching the surface increases by 30 to 50%. Plants are being damaged. Pollen malformation rates spike. Photosynthesis becomes less efficient. Primary productivity, the base of the food web, begins to decline on both land and sea. This is the phase where 96% of marine species go extinct. Not all at once, but in a cascading wave as each extinction destabilizes the species that depended on it. The reef communities collapse first, taking with them the countless species that lived in and around reefs. Then, the open ocean plankton, the base of the marine food web, crash as acidification and anoxia spread. Fish, ammonoids, and marine reptiles follow. On land, large herbivores starve as plant communities collapse. Predators, deprived of prey, follow them into extinction. This is the bottleneck, the filter through which only the toughest, most adaptable, or luckiest species pass. Phase 4, from 200,000 to 500,000 years, is the aftermath. The worst is over. Most species that were going to go extinct have already done so. But the planet remains in crisis mode. The Siberian traps are still erupting, though the intensity has decreased. Atmospheric CO2 remains elevated. Temperatures remain high. The oceans remain acidic, anoxic, and toxic. Hydrogen sulfide is bubbling out of the water and poisoning coastal environments. The ozone layer remains depleted, bombarding the surface with UV radiation. The survivors are not the diverse, specialized organisms of the Permian. They're generalists, opportunists, disaster taxa that can tolerate extreme and variable conditions. Lystrosaurus dominates terrestrial vertebrate communities, making up 95% of individuals in some fossil assemblages. In the oceans, small, simple mollusks and disaster-adapted foraminifera spread across the barren seafloor. These are impoverished ecosystems, low diversity, low complexity, dominated by a few hardy species. But they're alive, and that's what matters. Phase 5, from 500,000 to 1 million years, marks the gradual winding down of the eruptions. The last fissures seal. The flow of lava and gas slows, then stops. But the planet does not heal quickly. Atmospheric CO2 levels remain elevated for hundreds of thousands of years. It takes that long for chemical weathering of rock and the burial of organic matter to draw down the excess carbon. Temperatures begin to decline, but slowly. The oceans begin to re-oxygenate, but full recovery will take millions of years. The ozone layer begins to heal as stratospheric chemistry gradually removes the excess chlorine and bromine. If you compressed this million-year catastrophe into a single day, the peak extinction, phase 3, would last about 5 hours. The rest would be the slow build-up and the even slower recovery. And full ecological recovery? That 10 million year return to pre-extinction biodiversity levels? That would take 10 more days. By the time the planet had truly healed, 1,000 human civilizations could have risen and fallen. Carbon dioxide is a greenhouse gas. It traps heat. As CO2 levels rose from around 400 parts per million to over 2,000 parts per million, global temperatures climbed. 1 degree, 2 degrees, 5 degrees, eventually 8 degrees Celsius above pre-eruption levels. In the tropics, temperatures that were warm became unbearable. On the equator, daytime highs reached 50 degrees Celsius. 50 degrees. That's hot enough to cause hypothermia in most vertebrates within hours. There's no escape. Pangaea is so large that its interior is thousands of kilometers from any ocean. No sea breeze, no moderating coastal climate, just unrelenting furnace-like heat. Rainfall patterns shifted. The interior of Pangaea, already arid due to its sheer size, became a desert. Plants died. Without plants, herbivores starved. Without herbivores, predators followed. But this was just the beginning. The real killer was in the oceans. Carbon dioxide doesn't just stay in the atmosphere. About 30% of atmospheric CO2 dissolves into the ocean. When CO2 dissolves in seawater, it forms carbonic acid, H2CO3. The ocean's pH begins to drop. This is ocean acidification. Before the eruptions, seawater had a pH of about 8.2, slightly alkaline. As CO2 flooded the atmosphere and dissolved into the oceans, the pH dropped to 7.8, possibly lower in some regions. That might not sound like much, but pH is a logarithmic scale. A drop of 0.4 units represents a 250% increase in hydrogen ion concentration, a 250% increase in acidity. And for any organism that builds a shell or skeleton out of calcium carbonate, which includes most marine life, this is a death sentence. Calcium carbonate, KCO3, is the material corals use to build reefs, mollusks use to build shells, brachiopods use for their protective coverings, and countless microorganisms use to build their tiny skeletons. In alkaline water, calcium carbonate is stable. But as the water becomes more acidic, calcium carbonate dissolves. The chemical equilibrium shifts. Shells become thin, brittle. Larval organisms can't build shells at all. The energy cost of depositing calcium carbonate in acidic water exceeds what they can produce. They die before reaching adulthood. Coral reefs, structures that took millions of years to build, began to dissolve. The organisms that built them died. And it's not just the shell builders. As the oceans acidified, the entire marine food web collapsed. Phytoplankton, the microscopic algae that form the base of the oceanic food web, struggled. Many species couldn't maintain their cellular functions in acidic water. Zooplankton that fed on them declined. Fish that fed on zooplankton starved. Predators followed. Within 50,000 years of the eruption's beginning, 70% of marine species were gone. But the oceans had another surprise in store. Warm water holds less dissolved oxygen than cold water. It's simple physics. The solubility of gases decreases as temperature rises. As the oceans warmed by 8 degrees Celsius, oxygen levels dropped. Oxygen minimum zones, regions where oxygen concentration is too low to support most aerobic life, expanded. They spread from the deep ocean toward the surface, from the tropics toward the poles. And in these oxygen-starved waters, a different kind of life thrived. Anaerobic bacteria. Bacteria that don't need oxygen. In fact, bacteria that are poisoned by oxygen. These bacteria have a different metabolism. Instead of using oxygen to break down organic matter, the process called aerobic respiration, they use sulfate, a sulfur compound abundant in seawater. This process is called sulfate reduction. And the waste product of sulfate reduction? Hydrogen sulfide, H2S, the chemical that gives rotten eggs their characteristic smell. But hydrogen sulfide isn't just unpleasant. It's toxic to most aerobic life that needs oxygen. Concentrations as low as 500 parts per million can kill a human in minutes. It blocks the enzyme cytochrome C oxidase, which cells use to produce energy. Without that enzyme, cells can't produce ATP. They die. As the oceans warmed and oxygen levels dropped, anaerobic bacteria bloomed. They formed vast mats on the seafloor and in the water column. Hydrogen sulfide concentrations rose. And in a feedback loop from hell, the H2S began to poison the remaining aerobic life. Fish that survived the warming and acidification now swam into waters that were literally toxic. They died. Their bodies sank. Bacterial decomposition consumed more oxygen. The anoxic zones expanded further. Now here's where it gets truly nightmarish. At high enough concentrations, hydrogen sulfide doesn't just stay in the water. It begins to bubble out of the ocean and enter the atmosphere. The oceans had turned into a planetary scale hydrogen sulfide generator. Imagine standing on the coast 251 million years ago. The sky is hazy with volcanic gases and ash. The sun is a dim reddish disk. The ocean has changed color. Instead of blue, it's a murky green or purple, tinted by blooms of photosynthetic sulfur bacteria that thrive in the anoxic, sulfide-rich water. These are purple sulfur bacteria and green sulfur bacteria, ancient organisms that use hydrogen sulfide instead of water for photosynthesis. They're painting the oceans the color of bacterial metabolism. And the smell, the pervasive, choking stench of decay. That's hydrogen sulfide. It's being released by oceans that have turned into planet-spanning bacterial mats. On land, hydrogen sulfide is toxic to most plants and animals. Forests that survive the heat now die from the poison drifting inland on the wind. Herbivores that adapted to the new, hardier plants now have nothing to eat, and the die-off accelerates. Let me show you exactly how we know this. How scientists can look at rocks 252 million years old and reconstruct ocean chemistry, atmospheric composition, and even the specific mechanisms that killed organisms. It comes down to chemistry preserved in stone. Start with carbon isotopes. There are two stable isotopes of carbon, carbon-12, which has 6 protons and 6 neutrons, and carbon-13, which has 6 protons and 7 neutrons. That extra neutron makes carbon-13 slightly heavier. When organisms take up carbon through photosynthesis in plants or by eating other organisms, they preferentially use carbon-12 because it's lighter and requires slightly less energy to process. This means organic matter, anything that was once alive, is enriched in carbon-12 relative to the inorganic carbon in the environment. When geochemists measure the ratio of carbon-12 to carbon-13 in ancient rocks, they're reading a record of the carbon cycle. In limestone, calcium carbonate that precipitated from seawater, the carbon isotope ratio tells you about the balance between organic carbon burial and volcanic carbon release. At the Permian Triassic boundary, something dramatic happens to this ratio. There's a sharp negative excursion, a spike in the amount of carbon-12 relative to carbon-13. The excursion is about 5 to 6 per mil, meaning the ratio shifted by 5 to 6 parts per thousand. That might sound small, but in isotope geochemistry, it's enormous. What does it mean? It means a massive amount of organic carbon, carbon that had been in living things or buried underground, was suddenly released into the ocean and atmosphere. The magnitude of the excursion tells us approximately how much. Something on the order of 15,000 to 30,000 gigatons of carbon. And the shape of the curve, how quickly the ratio spiked and how long it took to return to baseline, tells us this happened over a few 100,000 years. This is the chemical fingerprint of the Siberian traps burning through coal beds and the die-off of most of Earth's biomass. Oxygen isotopes tell a different story, the story of temperature. The ratio of oxygen-16 to oxygen-18 in calcium carbonate shells depends on the temperature of the water when the shell formed. It's a thermometer preserved in stone. Colder water incorporates more of the heavier isotope, oxygen-18. Warmer water incorporates more of the lighter isotope, oxygen-16. By measuring this ratio in fossil shells from brachiopods, conodonts, and other organisms, researchers have reconstructed ocean temperatures across the Permian Triassic boundary. The data show a warming of 8 to 10 degrees Celsius in tropical waters. Some studies suggest even higher warming, up to 14 degrees in coastal environments. This is consistent with massive greenhouse gas release and matches climate model predictions for what happens when you double or triple atmospheric CO2. The work was painstaking. Teams of researchers spent decades collecting samples from Permian Triassic boundary sections around the world. In China, at the Meishan section, the global stratotype section and point for the boundary, geochemist Yin Hongfu and his colleagues collected samples every few centimeters through the boundary interval. Each sample was analyzed for carbon isotopes, oxygen isotopes, and trace elements. The pattern that emerged was consistent across sites in China, Iran, Italy, Greenland, South Africa. The isotope excursions happened at the same time, in the same sequence. This wasn't a local phenomenon, it was global. Sulfur isotopes add another layer to the story. Sulfur exists in multiple isotopes, with sulfur-32 and sulfur-34 being the most common. When bacteria reduce sulfate, using it as an energy source in the absence of oxygen, they preferentially use sulfur-32, leaving the remaining sulfate enriched in sulfur-34. This fractionation is the signature of anaerobic metabolism, and it's preserved in pyrite, iron sulfide fool's gold, that precipitates in anoxic sediments. Late Permian marine sediments show exactly this signature. Massive deposits of pyrite with sulfur isotope ratios that scream bacterial sulfate reduction. The oceans had turned anoxic, and sulfate-reducing bacteria were thriving. But there's more. Biomarkers, molecular fossils, provide direct evidence of which organisms were present. When cells die, their membranes break down, but some of the lipid molecules are remarkably stable. Hopanoids from bacterial membranes and steranes from eukaryotic membranes can survive in rocks for billions of years. In late Permian and early Triassic rocks, geochemist Clete Grice and her team at Curtin University in Australia found something remarkable: a spike in isorenuretane, a biomarker produced by green sulfur bacteria. These bacteria only thrive in the presence of both light and hydrogen sulfide. Finding their biomarker means the photic zone, the sunlit surface layer of the ocean, contained hydrogen sulfide. The ocean wasn't just anoxic at depth. Toxic, sulfide-rich water had reached the surface. It's direct molecular evidence for the killer oceans hypothesis proposed by paleontologist Peter Ward. And then there's the pollen. Fossil pollen and spores from late Permian rocks show abnormally high rates of malformation. Paleobotanists examining samples from Greenland found pollen grains with thickened or thinned walls, irregular shapes, tetrads that failed to separate properly. The malformation rates, the percentage of deformed pollen, spike from a background of about 2 to 5% up to 25 to 30% at the extinction boundary. Modern experiments have shown that UVB radiation causes exactly these kinds of deformities. Expose living plants to elevated UVB, and you get the same malformed pollen. The only way to get globally elevated UVB is if the ozone layer was compromised. And we know chlorine and bromine were released because we can measure them in fluid inclusions, tiny bubbles of ancient atmosphere trapped in volcanic minerals from the Siberian traps. The most dramatic evidence comes from the fossils themselves, or rather, from their absence. Paleontologists have studied hundreds of Permian Triassic boundary sections, counting species through time. The pattern is consistent and terrifying. In the late Permian, marine diversity is high, hundreds of genera. Then, within a stratigraphic interval representing perhaps 10,000 to 100,000 years, diversity crashes. In some sections, you go from 50 species to 3. Trilobites disappear completely. 96% of marine genera go extinct. On land, the Karoo Basin in South Africa provides the best record. In late Permian rocks, you find diverse assemblages of gorgonopsians, dicynodonts, pariasaurs, and therocephalians. In early Triassic rocks, you find Lystrosaurus and almost nothing else. The extinction is written in the rocks with brutal clarity. But there's one more killer we haven't fully explored yet. One that came from the salt deposits deep underground, released when the magma of the Siberian traps intruded and heated them. Chlorine and bromine. These halogens rise into the stratosphere, and once they're up there, 15 to 35 kilometers above the surface, they do something catastrophic. They destroy ozone. Ozone, O3, is a molecule made of 3 oxygen atoms. It exists primarily in the stratosphere, forming a layer that acts as Earth's shield against ultraviolet radiation. The sun emits UVA, UVB, and UVC radiation. UVA is relatively harmless, but UVB and UVC are highly energetic. They break chemical bonds, they damage DNA. Without the ozone layer, these wavelengths reach the surface at full intensity, and they're lethal. Chlorine destroys ozone through a catalytic reaction. A single chlorine atom can destroy thousands of ozone molecules before it's removed from the stratosphere. The reaction is elegant in its simplicity and terrifying in its efficiency. Chlorine, Cl, reacts with ozone, O3, to form chlorine monoxide, ClO, and molecular oxygen, O2. Then the chlorine monoxide reacts with a free oxygen atom, O, to form molecular oxygen and regenerate the chlorine atom. The chlorine is not consumed. It goes on to destroy another ozone molecule and another and another. It's a chain reaction. As the Siberian traps pumped chlorine and bromine into the atmosphere over hundreds of thousands of years, the ozone layer thinned. In some regions, particularly over the poles and at mid-latitudes where atmospheric circulation concentrated the halogens, the ozone layer disappeared entirely. Without the ozone shield, ultraviolet radiation flooded the surface. UVB radiation the most damaging wavelength that reaches significant intensity at Earth's surface, breaks the bonds in DNA molecules. When DNA absorbs UVB, it creates thymine dimers, abnormal bonds between adjacent thymine bases in the DNA strand. These dimers distort the DNA structure. Most of the time, cellular repair mechanisms can fix them. But when UV exposure is intense and prolonged, the repair mechanisms are overwhelmed. Mutations accumulate. Cells die. Organisms die. Plants on land are particularly vulnerable because they can't hide from the sun. They need sunlight for photosynthesis. But UVB radiation damages chlorophyll and the proteins in chloroplasts that carry out photosynthesis. The plants can't photosynthesize efficiently. Growth slows. Many die, and we have direct evidence of this. The combination of all these factors, warming, acidification, anoxia, hydrogen sulfide poisoning, UV radiation, created a perfect storm of death that nothing could escape. In the oceans, 96% of all species went extinct. Trilobites, survivors of 4 previous mass extinctions, creatures that had thrived for 270 million years, vanished completely. Not a single species made it into the Triassic. Think about what that means. Trilobites had weathered the late Ordovician extinction, which killed 85% of marine species. They'd survived the late Devonian extinction, which killed 75% of species. They'd made it through 2 smaller extinction events in the Carboniferous. For 270 million years, they'd proven they could adapt, evolve, and survive whatever the planet threw at them. But the Permian extinction was different. It wasn't a single catastrophic event they could wait out. It was a fundamental change in the chemistry of the ocean and atmosphere that lasted for hundreds of thousands of years. There was nowhere to hide, no refuge. And so, they died, every last one. Reefs collapsed. On land, 70% of vertebrate species disappeared. The Gorgonopsians, those magnificent saber-toothed predators that had ruled Permian ecosystems, extinct. Most dicynodonts, extinct. The forests, gone. What replaced them for millions of years was a world dominated by fungi. Fossil records from the earliest Triassic show something extraordinary and eerie. Coal seams, which are formed from compressed plant material, virtually disappear. Why? Because there weren't enough plants to form coal. But fungal remains are everywhere. Spores, hyphae, the thread-like structures of fungal bodies. For perhaps 2 million years, the dominant macroscopic life on land was fungal. Earth became a planet of mushrooms, feeding on the corpses of a dead world. But life, as it always does, survived, in small pockets, in refuges. And slowly, painfully slowly, it began to recover. The first organisms to return in significant numbers after the peak of the extinction were the decomposers and the extremophiles. Fungi, as I mentioned, thrived. They were breaking down the vast quantities of dead organic matter covering the land, releasing nutrients back into the soil. In the oceans, microbial mats, layered communities of bacteria and algae, spread across shallow seafloors. These structures, called stromatolites when they fossilize, were common in the Precambrian, billions of years ago, before complex life evolved. But in the early Triassic, they returned. It was as if evolution had been reset to an earlier chapter. The complex ecosystems were gone, replaced by the simple ones that had dominated ancient Earth. But slowly, painfully slowly, complexity returned. Small bivalves, clam-like mollusks, began to reappear in the fossil record about 1 million years after the extinction. They were generalists, able to tolerate wide ranges of temperature, salinity, and oxygen levels. Not the specialized reef builders of the Permian, but survivors. Gastropods, snails, crept back into the fossil record. Small, simple forms at first, then gradually more diverse. Ammonoids, which had been reduced to just one or two surviving lineages, began to radiate into new forms. Within 5 million years, there were dozens of new ammonoid species, each evolving to fill a slightly different niche in the recovering oceans. On land, Lystrosaurus wasn't alone for long. This decinodont, about the size of a pig, with a barrel-shaped body, sprawling legs, and a beak for cropping vegetation, was a survivor. It was a burrower, which meant it could escape the worst of the heat and the atmospheric poisoning by retreating underground. It was a generalist herbivore, able to eat almost any plant matter. And it was tough. In the earliest Triassic, Lystrosaurus made up 95% of all terrestrial vertebrates. 95%. Entire ecosystems consisting almost entirely of this one species. You'd walk across the landscapes of the early Triassic and see Lystrosaurus everywhere. Herds of them grazing on the scrubby vegetation, digging burrows, raising young. It's not that Lystrosaurus was particularly well adapted to the post-apocalyptic world. It's that almost everything else was dead. But from that bleak beginning, life diversified. Other decinodonts began to appear. Canamayeria, a decinodont the size of an ox, became common in the Middle Triassic. Archosaurs, the group that includes crocodiles, pterosaurs, dinosaurs, and birds, began their rise. Early archosaurs were small, agile predators. Euparkeria, for example, was about the size of a large dog, with long hind limbs suggesting it could run bipedally when needed. It had sharp teeth and a lightly built skull, an efficient predator in a world where prey was still recovering. These early archosaurs were experimenting with body plans. Some became heavily armored herbivores, like the etosaurs. Some became sprawling, crocodile-like ambush predators. And some, a group called the Avimatatasalians, began to develop upright postures, with legs tucked directly under the body rather than sprawling out to the sides. This posture is more energy efficient. It allows for sustained locomotion. And it's the posture that would eventually lead to dinosaurs. But dinosaurs didn't appear immediately. The first true dinosaurs show up in the fossil record around 230 million years ago, roughly 22 million years after the Permian Extinction. 22 million years. That's how long it took for ecosystems to recover enough complexity to support the kind of diverse, multi-level food webs that could give rise to dinosaurs. And even then, dinosaurs weren't dominant. For the first 20 million years of their existence, they were minor players, small, bipedal predators and herbivores living in the shadow of larger archosaurs and synapsids. It wasn't until the end of the Triassic, around 201 million years ago, that dinosaurs began their rise to dominance. And that rise was triggered by, you guessed it, another mass extinction. The Triassic-Jurassic extinction event, likely caused by massive volcanic eruptions associated with the breakup of Pangaea and the opening of the Atlantic Ocean, wiped out many of the large archosaurs and synapsids that had been dominating Triassic ecosystems. Dinosaurs, being smaller, more adaptable, and perhaps more efficient metabolically, survived. And in the aftermath, they radiated into every available niche. By the early Jurassic, dinosaurs were the dominant land animals on Earth. and they would remain so for the next 135 million years. So, let's put all three events side by side and compare them directly, because each tells us something different about how volcanic catastrophes unfold. Start with explosive power. Yellowstone's Huckleberry Ridge eruption wins this category decisively. 2,500 cubic kilometers ejected in perhaps 2 to 4 weeks. The magma chamber emptied catastrophically. The explosion would have been heard across North America. The eruption column likely reached 50 kilometers into the stratosphere, injecting millions of tons of sulfur dioxide into the upper atmosphere. Ash blanketed the western United States to depths of meters, and identifiable ash layers from this eruption have been found as far as the Gulf of Mexico. For sheer explosive violence, nothing in the geological record definitively exceeds Huckleberry Ridge. Some researchers have proposed that earlier eruptions, perhaps in the Ordovician or Precambrian, might have been larger, but the evidence is ambiguous. Huckleberry Ridge is the largest explosive eruption we can confidently document. Toba is second in explosive power, but first in documented human impact. 2,800 cubic kilometers ejected, slightly more than Yellowstone. The eruption created a volcanic winter that lasted 6 to 10 years. Global temperatures dropped 3 to 5 degrees Celsius. Sulfur dioxide in the stratosphere formed sulfuric acid aerosols that reflected sunlight back into space. For comparison, the eruption of Mount Pinatubo in 1991, a VEI-6, injected 20 million tons of sulfur dioxide into the stratosphere and cooled the planet by 0.5 degrees for 2 years. Toba injected an estimated 5 billion tons. That's 250 times more sulfur dioxide, with correspondingly greater and longer-lasting cooling. The genetic bottleneck in humans around 70,000 years ago is well documented. We went from a global population of perhaps several 100,000 to as few as 3,000 individuals. Every human alive today, all 8 billion of us, descends from those survivors. That makes Toba the single most important event in recent human evolution. Without Toba, human history might have unfolded very differently. We might have diversified into multiple species as we spread across the world, the way our hominin ancestors did. Instead, the bottleneck kept us genetically homogeneous, and when we finally expanded again, we did so as a single, closely related population. The Siberian traps are in a category of their own. By volume, they're unmatched. 1 to 4 million cubic kilometers of lava over 1 million years. That's 1,000 to 1,600 Yellowstones. But they weren't explosive. There was no single cataclysmic eruption, no towering plume of ash, no volcanic winter from sulfur aerosols. Instead, it was a slow poisoning. Flood basalt eruptions like the Siberian traps don't produce explosive eruptions because the magma is low in silica and gas content. It simply pours out of fissures and spreads across the landscape. The lava flows themselves covered 7 million square kilometers. But as I've explained, the lava was almost incidental. What mattered was the gas. Carbon dioxide from burning coal beds, sulfur dioxide creating acid rain, chlorine and bromine destroying the ozone layer, and the cascading effects: ocean warming, acidification, anoxia, hydrogen sulfide release. Each mechanism fed into the next, creating a feedback loop that lasted hundreds of thousands of years. In terms of death toll, the Siberian traps are the undisputed worst. 96% of marine species extinct, 70% of terrestrial vertebrates extinct. The only comparable event is the Ordovician extinction, which also killed around 85% of species. But that event was caused by glaciation and ocean chemistry changes, not volcanism. The Cretaceous-Paleogene extinction, the asteroid that killed the dinosaurs, eliminated 75% of species. Devastating, but not as severe as the Permian. And recovery time tells the same story. After Toba, human populations rebounded within 10,000 years. After Yellowstone, ecosystems were indistinguishable from pre-eruption conditions within 10,000 years. After the Siberian traps, it took 10 million years for biodiversity to recover to pre-extinction levels. 10 million years. That's 1,000 times longer. So which was the largest? If you mean explosive power, Yellowstone. If you mean total eruptive volume, Siberia. If you mean impact on life, also Siberia. But here's the critical distinction. Explosions are dramatic, but chemistry is deadly. Yellowstone and Toba were bombs. They went off, caused immediate devastation, and then the Earth's systems recovered relatively quickly. The Siberian traps were a slow-motion chemical apocalypse. The eruptions lasted so long that the Earth's climate and ocean chemistry were fundamentally altered for hundreds of thousands of years. Species couldn't adapt fast enough. There was no waiting it out. And that's why the Permian extinction was the worst. It wasn't the biggest bang. It was the longest, most comprehensive poisoning of the planet's life support systems that we know of. So here's the profound lesson from the Permian extinction. Mass extinctions don't just kill. They reshape. They remove the dominant groups and give opportunities to the marginal ones. Before the Permian extinction, synapsids, our ancestors, were the dominant land animals. After the extinction, archosaurs rose to prominence, and they would dominate for the next 150 million years. Before the Cretaceous-Paleogene extinction, the asteroid that killed the non-avian dinosaurs, dinosaurs were the undisputed rulers of terrestrial ecosystems. After that extinction, mammals, which had been small nocturnal creatures for over 100 million years, radiated and filled the niches left vacant by the dinosaurs. Each extinction is a tragedy for the species that die, but it's an opportunity for the survivors. Evolution doesn't have foresight, it doesn't plan, but it's relentless. Given time and empty niches, life diversifies. And sometimes the survivors of one catastrophe become the architects of the next great age. Without the Permian extinction, archosaurs might never have dominated. Dinosaurs might never have evolved. And without the Cretaceous extinction, mammals might still be small nocturnal insectivores. We exist because of mass extinctions, and that's both humbling and terrifying. Now, let's bring this back to the present day, because everything I've told you about the Permian extinction, the mechanisms, the timescales, the chemical changes, has direct relevance to what's happening right now. The Siberian traps released between 15,000 and 30,000 gigatons of carbon dioxide over 1 million years. That works out to an average of about 15 to 30 gigatons per year. Humanity is currently emitting approximately 40 gigatons of CO2 per year. 40. Do the math. At our current rate, we'll emit the equivalent of the Siberian trap's entire carbon output in roughly 500 years. 500 years versus 1 million years. We're replicating the carbon release of the worst extinction event in Earth's history, but doing it 2,000 times faster. The mechanisms are eerily parallel. The Siberian traps warmed the planet by 8 degrees Celsius over several 100,000 years. We've already warmed the planet by 1.2 degrees Celsius since pre-industrial times, and we're on track for 2 to 4 degrees by the year 2100 if emissions continue at current rates. The Intergovernmental Panel on Climate Change projects that under a high emission scenario, we could see 5 degrees of warming by 2200. 5 degrees in 300 years. The Siberian traps took hundreds of thousands of years to achieve 8 degrees. We're approaching that on a timescale that's a tiny fraction as long. The Siberian traps acidified the oceans. We're acidifying them now. Ocean pH has dropped from 8.2 in pre-industrial times to 8.1 today. That represents a 30% increase in hydrogen ion concentration, a 30% increase in acidity. And it's happening faster than at any point in the last 300 million years. Pteropods, tiny swimming snails that are a critical food source for fish, seabirds and whales, are already showing shell dissolution in the Southern Ocean and parts of the North Pacific. Their shells are literally being etched away by acidic water. Coral reefs are bleaching and dying at unprecedented rates. The Great Barrier Reef has experienced 5 mass bleaching events since 1998, with 3 occurring in just the last 7 years. 50% of the reef's coral cover has been lost. If current trends continue, most tropical coral reefs will be dead by 2050. And coral reefs support 25% of all marine species, despite covering less than 1% of the ocean floor. When the reefs die, a quarter of marine biodiversity goes with them. The Siberian traps created oceanic dead zones as warming water lost oxygen. We have dead zones now, and they're expanding. The Gulf of Mexico has a seasonal dead zone the size of New Jersey, caused by nutrient runoff and warming water. The Baltic Sea has permanent anoxic zones, covering tens of thousands of square kilometers. The Arabian Sea's oxygen minimum zone has grown by 15% since 1960. Fish and shellfish that once thrived in these waters are being pushed into smaller and smaller regions where oxygen is sufficient. Fisheries are collapsing, not just because of overfishing, though that's a factor, but because the water itself is becoming uninhabitable. And on land, the extinctions are accelerating. The current rate of species loss is estimated conservatively at 1,000 times the background rate, the natural rate of extinction in the absence of human impacts. Some estimates put it as high as 10,000 times the background rate. We're losing species faster than we can discover and catalogue them. Insects, the most diverse group of animals on Earth and critical pollinators and decomposers, are in precipitous decline. A 2017 study in Germany found that flying insect biomass had declined by 75% over 27 years in protected nature reserves. 75%. That's not in farmland or cities, but in protected areas. Similar declines have been documented in Puerto Rico, the UK, and elsewhere. Insects are food for birds, bats, amphibians, reptiles, and small mammals. If the insects go, entire food webs collapse. We're living through the opening phase of a mass extinction. Scientists call it the 6th extinction. The first 5, the Ordovician, Devonian, Permian, Triassic, and Cretaceous extinctions, were caused by asteroids, volcanic eruptions, and shifts in ocean chemistry. Natural catastrophes. This one is caused by us, and we're only at the beginning. The Permian extinction took about 200,000 years to fully unfold after the Siberian traps began erupting. We've been industrially emitting CO2 for about 200 years, 1,000th as long. If the trajectory continues, if we emit carbon at current or accelerating rates for another few centuries, we won't just replicate the Permian extinction. We'll exceed it, because we're moving faster than any natural geological process ever has. Now, let's talk about the volcanoes people actually worry about. Yellowstone, Campi Flegrei in Italy, Toba. Are these real threats? Yes. Should we be terrified? No. Let me explain. Yellowstone is monitored more closely than any volcanic system on Earth. The Yellowstone Volcano Observatory runs dozens of seismometers, GPS stations, and ground deformation sensors. They measure every earthquake, every millimeter of ground movement, every change in gas emissions. If Yellowstone were preparing to erupt, we'd know. There would be months, probably years, of precursor activity. Earthquake swarms, rapid ground uplift, changes in the chemistry of hot springs and geysers. We'd have time to evacuate. Not enough time to prevent the eruption, but enough to save lives. And the probability of a super eruption at Yellowstone in the next century is, as I mentioned, vanishingly small. 0.00014%. You're more likely to be killed by a lightning strike, a shark attack, and an asteroid impact in the same year than to witness a Yellowstone super eruption in your lifetime. Campi Flegrei, near Naples, is more active. It's a caldera that last erupted in 1538. The ground has been rising and falling for decades, a phenomenon called bradyseism. Earthquakes are frequent. 500,000 people live within the caldera. If it erupts, it will be catastrophic for them. But it won't be a VEI 8. The magma chamber isn't large enough. It might be a VEI 6 or VEI 7, devastating locally, but not globally. Toba is dormant. There's no sign of an impending eruption. The magma chamber is still there, still partially molten, but it's not pressurizing. Toba might erupt again someday, tens of thousands of years from now, maybe longer. Supervolcanoes are real. They are dangerous, but they are rare and they are monitorable. The threat they pose is dwarfed by the threat we're creating ourselves. We spend billions studying volcanic hazards. We build early warning systems. We plan evacuations, and that's good. We should do that. But we're ignoring the slow-motion eruption happening right now, the one coming from our tailpipes and smokestacks, the one we can actually control. Here's the ultimate irony. We look at Yellowstone and imagine the catastrophe. Ash covering the continent, civilization disrupted, millions dead, and we say, we need to be ready for that. But we're not ready for the catastrophe we're causing, the one that's already begun. Because it's slow, because it doesn't have the visceral impact of a volcanic explosion, because it's easier to ignore. But the mechanisms are the same. Carbon dioxide warming the atmosphere, oceans acidifying, dead zones spreading, species going extinct at rates not seen since the Permian. The Siberian traps weren't trying to destroy the world. They were just geology. Magma rising, gases escaping, chemistry happening. No intent, no malice. Just physics and chemistry playing out over deep time. But we know what we're doing. We have the data, we have the models. We understand the carbon cycle, the greenhouse effect, ocean chemistry. We're not ignorant. We have the technology to change course. Solar power, wind power, Next-generation nuclear reactors, battery storage, electric vehicles, carbon capture. These exist. The Montreal Protocol proved we can coordinate globally to solve atmospheric problems. We phased out CFCs and saved the ozone layer. We can do it again. Let me be specific about what those solutions look like, because it's easy to talk abstractly about renewable energy and carbon capture without understanding what's actually possible right now, today, with existing technology. Solar power. The cost of solar photovoltaic panels has dropped by 90% in the last decade. In many regions, solar is now the cheapest form of electricity generation, cheaper than coal, cheaper than natural gas. Utility-scale solar farms in sunny regions can produce electricity for less than 3 cents per kilowatt hour. That's cheaper than almost any fossil fuel plant. And efficiency continues to improve. Modern solar panels convert over 22% of sunlight into electricity, up from 15% a decade ago. Perovskite solar cells, currently in development, promise efficiencies above 30%. The technology works. The economics work. The limiting factor is deployment speed and energy storage. Which brings us to batteries. Lithium-ion battery costs have fallen by 87% since 2010. Grid-scale battery storage is now economically viable for smoothing out the intermittency of solar and wind power. In South Australia, a 100-megawatt battery installation, the Hornsdale Power Reserve, has been stabilizing the grid since 2017, responding to demand fluctuations in milliseconds. It's been so successful that dozens of similar projects are now under construction worldwide. And battery technology continues to advance. Solid-state batteries, which replace liquid electrolytes with solid materials, promise higher energy density and faster charging. Sodium-ion batteries, which use abundant sodium instead of lithium, could make grid storage even cheaper. The technology is improving faster than most people realize. Wind power is similarly mature. Modern wind turbines are engineering marvels. Towers over 100 meters tall, blades longer than a football field, each turbine capable of generating 10 to 15 megawatts. Offshore wind farms, built in shallow coastal waters, can generate power at capacity factors above 50%, meaning they're producing electricity more than half the time. And unlike solar, wind often blows at night, complementing solar generation. Countries like Denmark and Scotland now generate more than half their electricity from wind. It's not theoretical, it's happening. Nuclear power deserves mention. I know it's controversial, but fourth-generation nuclear reactor designs address many of the concerns about earlier reactors. Small modular reactors, factory-built units that can be deployed in remote locations, are inherently safer than large reactors. Molten salt reactors can use thorium instead of uranium, and they can consume nuclear waste as fuel, solving the waste disposal problem. China is already operating experimental molten salt reactors. The United States, France, and Canada have multiple designs in development. Nuclear power is carbon-free, operates 24/7 regardless of weather, and has a smaller land footprint than any renewable source. The fear of nuclear disasters is understandable, but statistically, nuclear power has caused fewer deaths per unit of energy generated than any fossil fuel, including natural gas. Modern designs make meltdowns physically impossible. If we're serious about decarbonizing, nuclear has to be part of the conversation. Carbon capture and sequestration, CCS, is the technology of pulling CO2 directly out of the atmosphere or capturing it from power plant emissions and storing it underground. The Sleipner project in Norway has been capturing and storing 1 million tons of CO2 per year since 1996. It works. The challenge is scaling it up and making it economically competitive. Direct air capture, using chemical processes to pull CO2 directly from ambient air, is more expensive but improving rapidly. Climeworks, a Swiss company, operates direct air capture plants in Iceland and Italy. The captured CO2 is either stored underground or sold for industrial uses. It's not yet cheap enough to deploy at scale, but neither was solar power 20 years ago. And finally, reforestation. Trees pull CO2 out of the atmosphere and lock it in wood. Tropical reforestation projects in Brazil, Indonesia, and Central Africa have the potential to sequester billions of tons of carbon over the coming decades. The technology here is simple. Plant trees, protect them from logging and fire, and let them grow. The challenges are political and economic, convincing governments and landowners that forests are more valuable standing than cut down. But it's solvable. We know how to do this. We just need the will to do it at scale. And that brings me to the final point, the lesson of the Permian Extinction. Earth survived the Siberian traps. Life survived. It took 10 million years, but biodiversity recovered. New species evolved. New ecosystems emerged. The planet didn't care. On geological timescales, the Permian Extinction is a blip, a thin layer of rock marking a time when almost everything died, followed by the slow return of life. Earth will survive what we're doing too. Give it a few million years, and the biosphere will recover. New species will evolve to fill the niches we've emptied. The planet will be fine. But we won't. Human civilization has existed for roughly 10,000 years. 10,000 years of agriculture, cities, writing, technology. The Permian Extinction recovery took 10 million years. That's 1,000 human civilizations. 1,000 rises and falls of everything we've ever built. If we push the climate past the same tipping points the Siberian traps did, the recovery will happen on timescales that make human history irrelevant. We'll be long gone. There's a layer of rock forming right now at the bottom of lakes and oceans in sediments around the world. Future geologists, if there are any, will study it and give it a name. They'll call it the Anthropocene, the age of humans. And when they examine that layer, they'll see the signatures of our presence. A sharp spike in carbon isotopes, a sudden drop in biodiversity in the fossil record, layers of plastic and concrete, isotopes from nuclear weapons tests, the chemical fingerprints of industrial pollutants. And they'll ask the same question we ask about the Permian Extinction. What happened? Why did so many species disappear so quickly? And when they reconstruct the cause, when they realize it wasn't an asteroid or a supervolcano, but one species that changed the atmospheric composition faster than any geological process ever has, they'll ask another question. Why didn't they stop? They had the knowledge. They understood what was happening. They had the technology to prevent it. Why didn't they act? I want you to imagine something. Imagine you're a paleontologist 10 million years in the future. You're not human. Humanity is long gone. Maybe you're a descendant of crows, evolved into a tool-using, language-speaking species. Maybe you're something entirely unrecognizable, a lineage that emerged from the wreckage of the Anthropocene extinction. You're studying Earth's history, and you come across the late Holocene, our time. You see a sharp boundary in the rock. Below it, biodiversity is high. Coral reefs, rainforests, temperate forests, polar ecosystems, all thriving. Above it, there's a crash. 30 to 50% of species gone within a geological instant. 10,000 years, maybe less. You measure the carbon isotopes and see a massive negative excursion. You measure ocean pH and see rapid acidification. You find layers of plastic, concentrated heavy metals, and radionuclides from nuclear weapons tests. And you reconstruct what happened. You realize that one species, Homo sapiens, industrialized, burned fossil fuels, and changed the atmospheric composition faster than any volcanic event in the last 500 million years. You calculate that we released carbon 2,000 times faster than the Siberian traps. You see the same mechanisms: warming, acidification, anoxia, extinction. And you find something else. You find evidence that we knew. You find scientific papers preserved in geological strata, physical documents, digital storage media turned to stone. You find climate models, projections, warnings. You find evidence of international conferences, agreements, debates. And you realize they knew. They understood exactly what they were doing and what the outcome would be. And then you look at the carbon emission curves and see that they continued rising. They knew, and they didn't stop. What will you conclude about us? Will you see us as a tragic species, unable to overcome our evolutionary wiring, wired for short-term thinking, tribal competition, and resource exploitation in a world that suddenly required long-term planning, global cooperation, and restraint? Will you see us as a cautionary tale, an example of what happens when intelligence evolves faster than wisdom? Or will you see us as villains, a species that chose short-term wealth and comfort over the survival of millions of other species, and ultimately over our own descendants? I don't want that to be our story. And here's the thing, it doesn't have to be. We're at a unique moment in Earth's history. We're the first species with the cognitive capacity to understand planetary scale processes, the technological capability to alter them, and the moral capacity to choose a different path. We are, quite literally, the first species that can decide whether to cause a mass extinction or prevent one. That's both terrifying and empowering. Every other mass extinction in Earth's history was inflicted on life by forces beyond any organism's control. Asteroids, volcanoes, ocean chemistry shifts driven by plate tectonics. Life had no choice but to endure. But this time, the force driving the extinction is us, which means we can choose to stop. And the question I keep coming back to is, what kind of ancestor do you want to be? Do you want to be the generation that saw the catastrophe coming, understood it fully, had the tools to prevent it, and did nothing? The generation that condemned countless species and our own descendants to a diminished world because we couldn't muster the political will, the economic sacrifice, or the moral courage to act? Or do you want to be the generation that said, no, not on our watch? We inherited a thriving planet, and we're going to pass it on, diminished perhaps, but alive, still capable of recovery, still full of wonder. That's the choice, and the clock is running. We're not the trilobites. We're not the gorgonopsians. We're not passive victims of planetary catastrophe. We're the first species in Earth's history to understand what's happening while it's happening. We know the mechanism. We know the outcome if we don't change course. And we have the technological capability to alter our trajectory. The question isn't capability, it's will. Do we have the collective will to act? Or will we, like the Permian creatures, simply march into the heat and the acid and the poison because we can't imagine a different path? So to answer the question I posed at the beginning, what was the largest volcanic eruption in Earth's history? By explosive force, it was Yellowstone's Huckleberry Ridge eruption, 2,500 cubic kilometers in a matter of weeks. By total volume of lava, it was the Siberian traps, between 1 and 4 million cubic kilometers over 1 million years. By death toll and lasting impact, also the Siberian traps, 96% of marine species, 70% of terrestrial vertebrates, and 10 million years before full recovery. But the most important volcanic event, the one that matters most to us living today, is the one we're creating. The slow-motion eruption of carbon from fossil fuels buried millions of years ago. We're following the same script the Siberian traps did: warming, acidification, anoxia, extinction. But we're doing it 2,000 times faster, and unlike the Siberian traps, we can turn it off. The question is, will we? Thank you for watching. If this video gave you something to think about, please subscribe. In the next video, we'll explore the bizarre and alien creatures that emerged in the aftermath of the Permian Extinction, the ecological experiments of the early Triassic, and how they set the stage for the age of dinosaurs. I'll see you then.